Good morning, Tree. Good morning, Sydney. Good morning, DJ. Good morning, Lawani. Good morning, Sarah. Good morning, Munera. Good. I'm looking at you. Good morning, Eric. Good morning, Pushpita. Good morning, Sinead. Good morning, Maya. Good morning, Lena. The chat. Oh, there's more people. Okay. The chat. Uh, good morning, good morning, Lena. Good morning, Maya. Good morning, Munera for the double. Yes. Good morning, Sarah for the double. Good morning, Pushpita. Good morning, Ashley. Good morning, Sydney for the double. Good morning, Lawani for the double. Good morning, DJ for the double. Good morning, Erica. All right, we are okay. Okay. Oh, more people. Okay. Okay. Good morning, Monpreet. We will start in a second. Oh, good morning, Monpreet. Okay, awesome. Oh, and Kayla. Good morning, Kayla. Okay. Um, let's begin. Yes. Okay. Oh, and so again, I think I've said this. The exams are happening. Like I'm trying to not release any until I have them all done. They are progressing. They're not done. I'm hoping to be done with them soon. I'll keep you updated. Um, but I'll just leave it at that for the moment. But they're certainly going faster than last semester for anybody who anyway. Okay, so um oh yes, okay. So a quick word also, you are going to in lab today. I think you saw the posting from Professor Cologne. I think you know the like the lab procedures or the lab manual, whatever you want to call it. Like today in lab, it's gonna start getting labby in it. I may have mentioned this last week. Like you're gonna start doing circuits in lab today, and we're gonna be doing circuits in lab for a while, like it's several weeks. Um, of course, what we're talking about in lecture is electricity, and what you're going to be doing in lab is electricity. Um, the, I will caution you that the theory of what we're talking about here in lecture is right now is about electrostatics, about basically what a sitting proton does to another sitting proton or a sitting electron, the forces of attraction and repulsion between the charges. Eventually, those forces of attraction and repulsion between the charges start accelerating the charges and getting charges into motion, and the charges start flowing through things such as wires, and we call that flow electrical current, and we call the flow through the wires and the apparatus that we set up with them circuits. And that's what you're going to be doing in lab. And for many people, it's super fun. For many people, it's a really nice break in a way, or at least like a do-over from all this kind of abstract mathematics. What you're doing in lab will be really like, trying to get light bulbs to go on or etc. Um, and so I'm saying on the one hand, for many of you, again, it may feel like a fresh start. Like many of you, and many of you may have done some of this stuff before in other aspects of your life, which is cool. So it's about getting things to work and making measurements regarding current, voltage, and resistance. Uh, so I will caution you that at least at first, the theory that we're doing in lecture will not directly, for good and for bad, it will not really directly help you get these circuits to work at the beginning. I mean, the biggest concept to take away from the lecture right now is essentially that positives repel other positives and positives attract negatives. That's like why the circuit it works the way it does. I will even add to that, I suppose, something that many of you know, but is certainly fundamental to circuits, which is that charges are only going to flow nicely through conducting materials such as metals. So, sort of a big principle in the circuits is that things flow when there's a metal path for them to flow through. Sometimes there's choices in that path, sometimes not. But for sure, getting things to work, your big thing is going to be making sure at all times, is there actually metal from here to there to there to there and back home again? Okay. So I'm cautioning you that other than that, what you're going to be exploring and experiencing and figuring out in the lab for the next couple of weeks is is very lab based. It'll be like the fundamentals that emerge or that Professor Cologne tells you about voltage, current, and resistance in the lab. Eventually, you will see the material of the lab and the material of the lecture hooked together, and you'll see how it all relates. But today, is it today? Yeah, like starting today, just again to say, for some of you, this is going to be great news. Whether you're following what I'm doing in the lecture or not, today won't necessarily directly affect your experience in the lab. For others of you, that might be frustrating, for sure. I'll even admit that I was the kind of guy, I mean, I was better at the math than at lab myself. So when people started doing experimental things in lab that were about whether it works or not, I personally used to get very frustrated. It can be frustrating, but it helps to know that whatever you need to try to progress through the lab, for right now, will be provided in the lab context or will emerge in the lab context. Okay, so circuits. Okay, sorry, I'm looking at the chat. So circuits is what will start happening in lab, and again, and also you're gonna have a few weeks. Like you'll get used to them, yeah, and you won't have to rush them. Um, okay, so that's what's happening. But now in lecture, I want to get back to the theory of this, the electrostatic um, fundamentals of electrostatic fields. That's I'm going to turn the page in a minute. I'll change the view in a minute. But what we're here to discuss is electrostatic fields. The assumption I'm making is that most of you completed the homework that you started with me, that you started in the lab last week in the board meeting, right? The big exercise that asked you to add together um, the field contributions from 2 point sources, like what was due today. I'm going to look in a second, actually, how we did with that. But what was due today was, can you take the effect of this point source over here and add it to the effect of that point source over here in order to compute the electrostatic field at some other location over here? That's actually, and I guess I got the answer for you, I believe, at the end of Tuesday, and then you turned it in this morning. So I'm assuming now that we're gonna move from there, that we have a sort of introductory understanding of what it would mean to picture the field at some location in space due to a couple of other point sources of electrostatic field. That's what I'm okay. I'm going to pause for a second. I'm looking at the so I'm going to go from there. Now, I'm looking at the chat. Okay, fair enough. Thank you, chat person. I hear you about the Wi-Fi. Both two chat people about the Wi-Fi. I got you. Okay, I understand. Oh, yes, I just guess that's true. Okay. Hold on, and there's another thing in the chat about okay. Um, so this picture on the board is not a picture you've seen yet. It's sort of a goal of where we're heading for today. That's well, I'll say the goal is to move. Your homework was about field vectors. You added two field vectors together to get one resulting field vector. What we're going to do today is start evolving our discussion from field vectors to something called field lines. Okay, so it's all about fields now. So let me see what. Right. Okay. And I'm going to change the view in a second because I know this is distracting. It's just like a fun way to start. But so this slide says, um, uh, what my handwriting says is representing and computing E fields due to continuous charge distributions, i.e., okay, so this is like hard to read, I imagine, i.e., how do we deal with smooth collections of charges more than a couple of points? Okay, so let me pause on that for a second. And again, okay, I guess it's getting distracting here. Let me get into this. Yeah, what I'm saying here, you just did this homework. The homework was a big calculation. It was a very important calculation. Um, but it was a lot, right? The calculation again was you had a dot of charge over here, a point source over here of some kind, positive. Then you had another point source over here, negative, and you were figuring out the field over here. In other words, the belief is that each one of these created a vector at the location you were looking at, and the vectors added together, and you got the final vector, right? Well, let me remind you of a couple of things about that. Number one, the real belief, and I'm going to give you diagrams about this in a second, the real understanding that we have is that each one of these dots, they didn't just place a vector over there at the point that you happen to be calculating or looking at. The idea is that each one of these dots placed a vector everywhere in space. That's the idea of the field, that the minute a proton exists in the world, anywhere, it tells the whole world that it's there by placing a vector at every single place in space, a vector that has size and direction, a vector at every single point in space that says, essentially, well, it says if you happen to be a 1 positive coulomb of test charge and you find yourself at my location, you're going to be pushed in a certain direction, a certain amount by that proton that's over there. In other words, a proton that exists in space places an arrow every point in space, and the arrow, of course, it's not a literal arrow, but like in our minds, there's this arrow sitting there at every point in space containing two key vital pieces of information. How big of a charge is somewhere over there and precisely where it is, right? So if you exist, you deposit your vital stats, how big you are, if you're a charge, right? Or a mass, but if you're a charge, how big you are and where you are, you place that in a little arrow everywhere in space, right? So Q1 in your homework that you did, Q1 made a field of arrows everywhere in the universe just by virtue of its existence. And Q1 made its own field of arrows everywhere in the universe. And then, so any point you looked, you would find two arrows there adding together and therefore a resulting arrow. And that's what you calculated in the homework. Like what I'm trying to emphasize right now is all the work you did was to add the effects of two arrows together at a certain point in space, but we just picked that point in space arbitrarily. We could have done that calculation for any point in space and we would have gotten an answer, a different answer, but an answer. And so all of that work was just to find out what's the effect of two dots on one location. So what I'm saying here on this slide is, wait a second. Okay, that's great. That makes sense that's how that works. But that's like a lot of work to do to figure out the effect of an effect, just like basically what all that work was that you did. And I'm not exaggerating here. If you really think about all the work you did to do that homework or that we did together, in a way, what it's amounting to is like, what would you feel if you stood somewhere near, if you stood somewhere near like a hydrogen atom, right? Like a proton and an electron, like if you stood somewhere near, what would you feel? So all of that work was just to get the effect of two dots, like a proton and an electron. Well, clearly the world is full of a lot more stuff than just like a hydrogen atom. So there's dots everywhere, and dots everywhere creating field, and we would want to know the field, or put another way, if a hydrogen atom is sitting here, I don't just want to know the impact of the hydrogen atom, like just at this one particular location over there. I'd want to know what the vectors from it are doing everywhere. There's got to be some kind of like pattern of vectors everywhere that I could stand back and look all at once and not have to go vector, 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 vector. I wouldn't want to have to redo that entire homework assignment for every single location that happened to be near one hydrogen atom, is what I'm saying. And furthermore, in the real world as we experience it, or as you're going to experience in the lab, you don't experience from a macroscopic, like human perspective, you don't experience like dot of charge, dot of charge, dot of charge, dot. You can the dots of charge are so close together from our perspective that they might as well be attached, right? We tend to not experience pixels of charge. We experience streams of charge, continuous distributions of charges that are so close together. As far as we could tell, the separation is like infinitely divisible, right? So the question is, and I'm going to turn the page, but the question is there a way, now that we know how to add two vectors together, is there a way that we can sort of zoom out and look at patterns of vectors in a big picture way rather than just grind individual vectors? And the answer is yes, there is a way we could do that. And it's called moving our attention from vectors to from field vectors. We're going to move our attention and our way of thinking from E field vectors to E field lines, which many of you have heard of. You've seen line diagrams and you'll see them today. They'll be familiar in a way, but you may just not have known exactly what they were. We're in our, so I'm going to turn the page, but I'm saying up until now, the way I understood a proton is the minute there's a proton in the world, it creates vectors everywhere in space. Now I've understood that that is a mental model. Like that's a metaphor in a way. Like nobody literally thinks there's little styrofoam arrows like sitting anywhere in space. What we think is that there's information everywhere in space, unthingy stuff, information. And a very convenient way we have in our minds of visualizing that information is as little arrows, because the information is of the form magnitude and direction. So arrows up until now have been a very convenient way to picture how information exists in space. Now I'm going to say there's even a more convenient way to think about it, or more convenient for other purposes, and it's called not arrows, but field lines. So, okay, so let me get specific now. Excuse me. Everything I'm saying, notice the white equation up at top. Everything I'm saying is all a way of visualizing or understanding or predicting, modeling the implications of that equation up at the top, like the white one, right? We're saying the electrostatic field due to some point source is the net electrostatic force per charge due to that point source, right? We're saying whatever field is, it's information, and it gets weaker and weaker as you get farther and farther away from the source charge. The bigger the source charge, the stronger the field, and the farther away, that's the Q in the numerator, and the farther away you are from the charge, the weaker the field. That's the R in the denominator, right? And it's all multiplied by that universal constant, 1 over 4 pi epsilon naught. Okay, so to be concrete and clear, I'm still talking about, so this is a reminder of the vector field diagram due to a positive Q point source. Like, so what I'm focusing in here on what I believe was going on with Q1 in your homework problem, right? Like there was like a bunch of protons squeezed together in a tiny dot at coordinates 5, 4 in the homework problem. And when I'm saying that, and you only cared about one of its field vectors, you cared about the field vector that it placed at the origin. But I'm saying now stand back a little bit in your mind and just look at what that Q1 was doing the minute it got into the universe or into the lab. That Q1 was creating arrows everywhere. And what I've drawn here is a representative sample of those arrows, right? Like I really believe there's arrows everywhere for any, I really believe that a field is a vector valued function that for any place you name, I could name the one and only arrow that is sitting there at that place. The arrow represents how hard and in what direction a test charge of 1 positive coulomb would be pushed or pulled due to this source, right? So look at the picture. You see the picture. I've picked just enough arrows, I feel. I picked a sort of standard number of hours, like 24 hours, just enough to kind of demonstrate the pattern of the arrows. What is the pattern that I mean? I mean two things. One, all of these arrows are pointing out from the charge, like literally along radial lines. That's not like just a design feat. Like that's not just because I think it looks pretty, or nor is it random. What it's saying is like if you picked a point, like point P, that red point, that ran the arbitrary point, representative point of point P. If you picked point, wait, is it recorded? Yeah, okay. If you picked point P and asked, okay, what if there was a positive 1 coulomb of test charge right there? Like, what would happen to it? So you look for the nearest arrow to point P, and you see there's an arrow pointing out along the line connecting plus Q to P in your mind. Like, I didn't draw that line. Maybe, I could. Like, first thing I do in my mind, the thing to get used to is I draw this little unit vector, right? R hat, this little unit vector that deliberately points from Q to P, from the source to the location of interest. It, and and then I build an electric field vector from that R hat, right? That's what the White equation says. You scale up that vector by a certain amount and then change its units by a certain amount in the constant. And next thing you know, you have a field vector that's of a different size, but pointing in the same direction. The direction is from plus Q to red point P. And it's saying that if you were at point P, you'd be shoved out along literally the direct. So in other words, if P is northeast of Q, then P would be pushed to the northeast, right? So all the arrows here are out along radial lines. That's the first piece of the pattern I want you to see. And they're out, they're pushing out literally because plus Q is a positive. In fact, right, okay? Like because positives push on positives. And the test charge that we imagine, the field is always a prediction of what would happen to a supposed positive test charge. Okay, so all these arrows are pointing out. But then the next thing you notice, and hopefully in a way, everything I'm saying you already know, but I'm just sort of saying how this picture is trying to capture what you already know. So this picture is trying to capture that no matter where you are in the region, in the neighborhood of plus Q, you'd be shoved out by plus Q. That's the first thing it's capturing. The second thing it's capturing is, notice, the vectors are getting smaller and smaller as we get farther and farther away. And they're not just getting smaller in a random way. Like, in other words, I'm going to erase this in a second, but like this vector here is smaller than that vector there, but by the same amount as this vector is compared to that vector, right? Like, what is that all about? That's all about the R squared in the denominator. It's saying once you pick a certain radial distance that you are from plus Q, the field is a certain weakness. The bigger the R, the weaker the field. Oh, okay. Yeah, right. Exactly. So someone just said that, thank you, and please give yourself points for this. Someone just said in the private chat, do the vectors get smaller because of the R value? That is 100% correct. That's exactly the point. Yes, good, good. Right. As R in the denominator gets bigger, the whole E field result gets smaller. And that is exactly what the lengths of the arrows are trying to capture, that pattern. And so that's really good. I'm excited. Thank you. And I'm going to move on, therefore, in a second. But I'm just trying to emphasize something that I often say in physics. I find myself saying a lot in physics these days because I actually think it's a a subtle point that escaped me for years. Like these kind of one of the reasons that I emphasize step one DFP so much, or emphasize free body diagrams or graphs or all these other diagram techniques that we do. I want to emphasize that these diagrams, they at some level, yes, they're rough sketches that just sort of help us visualize what's going on, which is super important because we're not just talking about math, we're talking about the physical world of space and time. But also, I want you to know it doesn't help that I'm not so, that many of you are far better, visual represent artists than I am. I want to emphasize that like these sketches that we draw, if we draw them with rulers and protractors, or if we use AI or a computer to generate them, right? The idea behind the drawings then is they're not, if they're drawn to scale, which they most certainly can be. If a vector diagram is drawn to scale, the idea is then that the diagram actually is a computational tool, right? It's not just a rough idea. It like literally is. So what I'm saying here is if we picked a scaling factor for these arrows and said, every centimeter of arrow length like actually represents uh um like a meter of space in actual space, or then getting more to the point, once we draw the arrows as field arrows, if we said every centimeter of an arrow represents 1 Newton per coulomb of field strength or something, right? Then the diagram would not only be very pretty and organized, but it would mean that if you're trying to figure out the field at a certain location, you would literally just go to that arrow and measure it and its measurement, and with a protractor you'd measure its angle, and like those numbers would literally tell you the field. Like, do you see so these representations are, they are the thing once you pick a scaling factor. So yes, that question that the person asked, do the vectors get smaller because of the R value? The answer is yes. And I'm trying to say, in fact, in a precise way, the more precisely you draw the drawing. Yes. Okay, so if you're following the reasoning, which at least one person most certainly is, that means if I'm going to draw the field vector diagram from a negative point source, as I have here, it's going to be the same pattern, the same picture, but now all the arrows are pointing in because we regard negative sources always as pulling. We regard positive sources as pushing, negative sources as pulling. Let me put it another way. We believe that positive point sources create repulsive fields, and negative point sources create attractive fields. And again, mathematically, that's because of the R hat. You start drawing all these arrows along the direction of R hat, which is from the point source to wherever you're looking, always, right? But then you plug in the numbers, Q and 4 pi epsilon naught squared. You plug in the numbers to scale that R hat vector into and turn it into a field vector, right? You plug in the numbers to stretch that 1 meter of displacement into some other value of newtons per coulombs. And then when you plug in those numbers, if the Q is a negative, if you're plugging in a negative charge for what's creating the field, then you plug in a negative sign. So you have negative R hat. Like then therefore you don't just scale R hat, you actually also flip R hat. So the arrows come back and indicate pulls. That's mathematics. Conceptually, I'm saying positives always create fields that push out and negatives create fields that pull in because, and again, I'm going to say this because I remember the 2 years when I was an undergrad that I did not know. This didn't sink in, even though I'm sure my professor said it a bajillion times. I'm going to say again, the reason that let me say it again, sources can be positive or negative. But the reason that positives always push out and negatives always pull in is because the test that you're considering is always positive. The field is a prediction of what would happen to a positive test. If it then ends up happening that a negative charge is in a field, it will be accelerated to the direction opposite of the field lines. or the field vectors. The field is predicting or representing what would happen to a positive receiver. Therefore, positive sources always push out, negative sources always pull in. Okay, so you have this diagram. Okay, now my handwriting, I'm looking at the chat. Okay, my handwriting, which is insane, at the bottom says, so okay, so right now we have what everything I just said, I'm looking at the time. Everything I just said was in theory like zooming in on the two charges from your homework and saying what are each of those individual charges doing according to vectors. Like, let me say that a different way. I'm saying I'm still like picture that problem you did for homework. Like, that's why you did it for homework. Like there's a lot going on there to think about, right? But again, for homework, I want to emphasize you took one of the arrows from one of these pictures and you added it to one of the arrows of the other picture, right? You took one arrow from each and added them together and did all that work to get one final arrow because you were looking at one particular location that we called 0, 0. So you were looking at the two arrows, one from each source that landed at that one location. So what I'm trying to do now, and you were thinking in terms of vectors. So I'm right here reminding you, okay, if we're still thinking of vectors, if you wanted to zoom out and sort of start understanding what any of the points in that Cartesian plane were experiencing, you would draw like probably, or at least I'm drawing like 24 arrows for each of the sources just to give an idea of the pattern, right? So I'm zooming out now on those two charts and saying this is what they're doing sort of in general. And anywhere I look in this Cartesian plane, I would find two, one arrow from each that would add together. And I would go through all that math to understand what's happening there. So this is like literally 48 arrows already I'm picturing in my mind just to get a sense of what's going on in the Cartesian plane in general, captured by that last problem that we solved. So what it says in blue down below is for larger, smoother situations, we zoom out and we consider the pattern of arrows. Okay, that is so illegible. Hold on one second. Okay, so I'm saying now, if we were to have an even larger situation, like instead of two dots, maybe three dots, maybe helium instead of hydrogen, maybe beryllium, or even better, if we're going to get more realistic, like we're getting into the lab now, what if we didn't just have like two dots or three dots or four dots? What if we had a bunch of dots, a huge bunch of dots, all really close together, forming a line of charge, as might exist in a wire, like in the lab today? Like, what if we just have a wire of charge? And I want to emphasize again, like in some ways, a wire of charge, just a simple wire sitting on your desk. And by the way, even before you turn the power on your lab desk, I mean, just like imagine a simple wire sitting on your lab table. Now, on the one hand, that's a ton of dots of charge. I mean, really, that's like millions and millions of dots of charge. So if we were to keep thinking, if we want to know the effect of that wire on any nearby spot, if we keep following the method of your homework, like you'll really hate me and I'll deserve it. Like, and I'll hate myself. Like if we have to keep adding vectors, no, wait, let me slow down for a second. I'm sorry. Let me make one. I'm saying if we had like a long line of charge, like in the lab, a wire of charge, and we wanted to know what's the effect of that wire on a nearby spot. On the one hand, before I get all sarcastic and silly, let me say what would happen, what the effect of that long wire on one nearby spot would be the vector sum of all of the vectors from all the dots in that line. I shouldn't be so mocking. Like the reason we just did that homework is that is the reality of what's going on. The net effect, the field at any one location is the vector superposition of all of the sources of that field nearby. So if you had a million dots all connected together into some smooth line, the effect nearby is the vector sum of all those vectors. Like that's why we learned how to add vectors together. But of course, right, I don't want to add that many vectors together, and neither do you. Like two took long enough. And furthermore, if you're in the lab, all these dots are all attached together. They're so close. It's not even a million dots anymore. It's just a line. So that in a way makes it even more complicated because in a way it means that we're now not adding anymore, we're integrating. So in a way that sounds to me even very intimidating. I don't mean even, but to me it sounds very intimidating. But on the other hand, and this is the way physics always goes, on the other hand, even on the one hand, a line is a collection of many, 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 many points. But on the other hand, if you stand back, a line is simple. I mean, a line is just a line. There's got to be some way of simplifying this whole situation so that I can regard a line as just a smooth line of charge and stand back and say, isn't one smooth line of charge doing something kind of simple in the same way that one dot of charge is doing? So the way I do that, the way I zoom out and I can is literally I zoom out and I look at what is the pattern of these arrows doing. Like not in, I don't want to grind each individual arrow. What are the arrows doing in general? So in my mind, I sew up, not just me, everybody sews up all the arrows. Like you see, there's like three arrows on each radial line. Three is just a representative number, but there's a bunch of arrows lying on each radial line. So I sew them up in my mind and make one big line. So I end up with a diagram that looks like this. Oh, okay. I see the chat. I'm going to pause for a second to take the chat. Just one thing to be clear. I'm now moving back. I'm like literally taking this diagram from the positive source. I'm changing it from a vector field diagram to now what we call a field line diagram, right? And I'm going to do the same thing to the negative. So the same thing, you can ignore the blue thing. I do the same thing to the negative where we have the same kind of pattern of radial lines, and from positive they go out, but from negative they go in. And I'm going to talk about what that means. So, I mean, it might not be, it's not vastly different, but it's a lot simpler because I've just went down, if nothing else, I've gone down from 24 arrows to 8 arrows. That's an improvement in simplicity. All right, I'm going to pause for a second. Sure. Yeah, I think this has come up. So I'm looking at the chat. Yeah, right. A very good way to think about this is like magnets. Yes, I mean it's like magnets. Someone is saying in the chat, and if that helps you think about this, that's good. It turns out that we're going to study magnets as well. It turns out that magnets are, in fact, made of lots and lots of little phenomena like this. So, uh, but yes, magnets are the concrete macroscopic uh, relatable manifestation of all of this. That's right. So if thinking of magnets helps, go for it. Yes. Okay, so that's good. I'm looking at else at the chat. Okay. I want you to notice, so I'm going to talk about this. So we're now shifting. Again, I this is going to be visual for a while. Like if you want a little breath of fresh air from calculus, like for a little while, that's what you'll have. We're talking about visualization now, and sure, like the suggestions in the chat of ways to visualize are helpful. We're so what we're saying is vectors is one way to visualize and compute and predict what field information will do. Now we're saying it turns out if you want sort of to capture more if you want to capture bigger and smoother realities, it turns out that sewing up the vectors and creating these things and visualizing these things called lines turns out to be a more customary, standard, more robust way of understanding the field. So we're moving in our representation from vectors to lines. I mean, it's like, well, I mean, it's kind of like once upon a time when we moved from viewing the world from number lines to vectors or something. Like it's just another way of trying to capture the same reality. So if we look at this, notice I still have a bunch of lines that are pointing radially from the pot. Whatever I do now, whatever I say, it's meant to be a different way of conveying the same information. The same information, meaning I still want to be able to answer the question at any given point in space. What is the magnitude and the direction of the field? Like how hard and in what direction would I be pushed if I were a positive 1 coulomb of test charge and I found myself at that location in space? So we still want to convey those same pieces of information, magnitude and direction. Well, we still have a bunch of lines here that seem to be, I mean, we still have a bunch of, lines that seem to be pointing in a certain direction, and that direction seems to be out. We still seem to have arrowheads, so direction still seems to be there in the picture, but do notice one subtlety. I've moved, and when we look at websites in a minute, and when you ever look at websites or ChatGPT or anything like that, you will, there's like slightly different conventions and nuances for this, but you'll find frequently the arrowheads in field diagrams don't anymore sit at the tip of the lines. There's a reason for that. They often sit in the center of the lines. And in fact, and this can differ from website to website, but often there'll be like lots and lots of tips, like sort of non-specific numbers of tips that just go on the lines. So it could be sometimes it's just one, sometimes it's many, but the point is that they're very rarely at the tips of the line. They're like in the center line. There's a reason for that I'm going to get to in a minute, but do notice that change, please. That's one thing. And the other thing is that notice, therefore, that the individual arrows are gone. They're no longer distinguished. We just have one line representing a whole bunch of arrows. And for a negative source would be the same thing, only pointing in. Now, this is a simpler picture, and you're going to see that the more complicated the situation gets, the more simple in comparison this becomes. So this becomes a more and more useful way of looking at things. The more the complicated, the smoother and the more complicated the situation is. But again, I remind you, for this picture to work, it's got to convey, precisely convey, like to scale, it's got to convey the same original things that vectors were meant to convey, which is magnitude and direction. So let's see if it really is doing that. So I'm going to go backwards now on purpose. Like first I'm going to look at direction. So the direction of of the field at any point in space is represented by the orientation, the arrowhead, of the corresponding line on the page. Okay, so let's pause. That's a lot of words, but I'm just saying what I think you already would guess. I'm saying we still have arrowheads, so direction seems to still be conveyed. And let's be specific, like what direction? The direction of the field at a point in space. If you want to know the direction of a field at a point in space, you look at the point on the page that represents that point in space, and you look to the line that you're nearest on the page, and wherever the arrow's going, that's where the field is going, just like you would expect. But now let me add one technicality to that you'll see in a minute, something that we didn't have to deal with vectors. Specifically, I'm going to say if you're trying to figure out the direction of the field on the page, you look at whatever line you're nearest, because again, the lines are everywhere, but we just draw just enough to represent the situation. So you look at whatever line you're nearest and you look at the direction of that line. Well, it's going to turn out, you're going to see in a minute, that these field lines could actually curve. They can be curved. Vectors are never curved. These lines can be curved. So if you're looking toward a line and it's curved, well, what's the direction that you pick? You do the same thing we've always done in calculus. You just imagine a line tangent to the curve at that point, because that is the direction of the line at that point. And the tangent line to the curve will give you the direction of the field. I'm not saying you have to calculate derivatives or anything like that, but I'm saying I'm just saying that what direction is a curved line heading at any point? It's heading the direction of its tangent line. So field lines can be curved, so we often visualize tangent lines to picture direction. But it's still all captured by those arrowheads. So the arrowheads tell us direction. But now, what about magnitude? This is a little bit more involved or interesting. So this says, how is the magnitude of E conveyed by field lines? So why is this like an issue? Well, because these are now field lines, they're not vectors anymore. The whole convenience of a vector, it was an arrow that had a certain orientation, tip tail orientation, and it had a certain length from the tail to the tip. The length of that arrow indicated magnitude of quantity, right? And you could always set up a scaling factor, like 1 centimeter of length of each arrow represents 1 Newton of force or something like that, right? But these lines don't have length anymore. They literally do not have length. It says in yellow, field lines, unlike vectors, do not have lengths in any meaningful way. Excuse me. In any meaningful way. What do I mean by that? I mean, like, of course, these lines have length. Like, I'm a human being. I had a piece of paper or a screen that eventually ran out of room, and my pen eventually ran out of ink. Like, yes, they have length, but they don't have length in any meaningful way. Meaning, as you get more and more into it, you'll see those lines, they only stopped because I ran out of ink or I ran out of space or whatever. One of the reasons that I shove the arrowheads into the middle of the lines is to remind the reader, and I'm not making this up, like why we all do this is to remind anybody who's looking at the field line diagram that the lines actually go on forever. We just stopped drawing them because we ran out of space on the page. But unless you see the line literally stopping at something, which I'll describe in a moment, if the line just seems to taper off, it's only because we stopped drawing. Like, what do I mean by that? I mean, if you put a proton in the universe, its effect carries through the whole universe. What do I mean by that? I mean, the thing that someone in the direct chat thankfully said 20 minutes ago, remember, there's an R in the denominator. The R in the denominator of the field function describes how strong the field is. Okay, I'm going to totally see. I see that in the chat. It looks great. I'm going to get it in 1 second. I'm just going to finish this point. You can plug any value you want into R, no matter how big it is. If it's a finite number, the whole field function will spit out some number, maybe very small, but still a non-zero number, which means I don't care how far away you are from a proton, you're being affected by the proton some amount. Now, maybe a very small amount. And maybe you're closer to other electrons near you that their effects dominate. And you end up sort of not caring that much about, but the field effects go on forever. So these lines, unless you literally see them hit another thingy thing in the drawing, which I'll get to in a minute, unless they literally land on another charge, if they're just sort of going off in space on the drawing, the idea is that they go on forever. That's a very important. Again, that is why we don't put the tips. Most people don't put the tips at the end of the line because we're trying to say there is no end of the line. Okay, so therefore, and then I'm totally going to get the chat thing. Therefore, I'm saying you could take a ruler and measure the length of these lines here, but it wouldn't tell you anything. That's just because that's when I stopped drawing. So I'm looking at the chat. So vectors have length, but field lines don't because they are technically infinite. That's what the chat says. And yes, that's awesome. I agree. Please give yourself points. That is what I'm saying. That's 100% what I'm saying. Field lines. Well, I'm going to say it even more specifically in a minute, but yes, field lines, unless they literally hit a charge, I'll be more specific about that in a minute. But if they don't literally start at a charge or land on a charge, they go on forever. That is right. Therefore, there is nothing about the length of a field line in a drawing that tells you anything about magnitude. That, I mean, so A, I agree with the person in the chat. I also still want to say, that I also agree with the person who said about magnets. I think the only reason I'm agreeing in like a different way is the person who said the thing about the magnets is like, that might not help like, if you heard that about magnets, you're like, wait, we're talking about magnets now? Like, I don't even know I don't even like magnets. Then you can ignore that because I'm not saying it's necessary. But yes, if it helps you, if you're like, oh, it's like magnets, then yes, that's awesome. But yes, I'm definitely also agreeing that field lines do not have length in any meaningful way. Therefore, it raises a question. Wait a second. So you might even say that, oh, well, this is why we didn't sew them up before. Or if you were thinking like, yeah, if these field lines are so great and if they're so much better than vectors, like, why didn't you just like start the class with field lines? Like, why did we ever bog down in vectors? I mean, there's many reasons for that. One of the reasons is I'm not saying the vectors are wrong. The vectors are still correct. And vectors are across the board in physics a really useful tool that we use like for everything. And when you're dealing with really dot by dot fundamental situations, vectors are the best way. But now I'm saying, okay, if we're going to zoom out and the situation is going to get more complicated, we want to like sew up those vectors, okay. But what we seem to lose when we sew up the vectors, what we seem to lose is magnitude information. We seem to now have no concept of magnitude anymore. And that would seem to defeat the whole purpose. But it doesn't, because if you look at this picture, there is a way. If you already, okay, I'm saying, remember, the farther away you are from a point source, the weaker the field is. Like that, I'm saying, actually, one of you said it in the direct chat like 30 minutes ago. These have been very tight, helpful comments. I appreciate it. The 30, like one of you said, because of the R in the denominator, the farther away you are from this plus Q, the weaker the field should be. Now, I'm saying if you look in this picture, this is a subtle point I'm about to make. If you look at this picture, I can't tell that anymore. Like there's nothing about the lengths of these lines that give me that sense. But there is something about this picture. And I'm going to ask you in the direct chat right now. This is a hard question, I think. It's not meant to be a trick, but it is tricky. I'm going to ask, and so at bet, even if you put in the chat, I hear what you're asking. I'm with you, but I totally don't know the answer. I would respect that deeply. So here's the question. If you look at this picture, there actually is something. Oh, and I see something in the chat. I'm going to look at it in 1 second, but I'll say this question. If you look at this picture, there is something going on subtly, whereas you get farther and farther away, something is changing in the picture versus when you get closer and closer. There's something in this picture that if we wanted to, we could turn into our way of telling. Like we could take seriously as our way of telling that closer to the charge, the field is stronger. Like there is something about this picture that I might not have noticed before that could be used to indicate strength of field. Like I'm going to say it again, then I'm going to shut up. Well, then I'm going to look in the chat, but then I'm going to look for more in the chat. I'm asserting that you know the field is stronger closer to the charge than it is farther from the charge. Now I'm asserting that actually something about this picture kind of gets that across once you pay attention to it. There's an aspect of this picture where something does seem like higher or bigger or stronger or something closer to the charge than farther away. I mean, take it to the limit in your mind, get really far away from the charge, and something is happening to the lines that is like different from what's happening to the lines closer to the charge. And if you can follow what I'm saying, I'd love suggestions in the private chat as to what that is. Like, what visual feature of this picture could we be using to tell how strong the field is? That's my question. I'm going to repeat it and then I'm going to look in the chat. And I know there's an old thing in the chat I'm going to look at, but I'm saying what visual feature of this picture could maybe be used to indicate or represent strength of field. Okay, so now I'm looking in the chat. Oh, okay. And I'm going to read. So something that was in the chat, like before I asked that question from on the other point, yeah, is good. Someone's saying in the chat, just for clarification, the field will weaken the farther away it gets, but it will never fully go away unless it hits a charge, right? So yes, 100%. Well, the field weakens as we get farther away, but it never fully goes away. That's correct. And then the part, very correct. Then the part where the person says, unless it hits a charge. I see why they're saying that. That totally shows they're paying attention to me because I keep saying that over and over. But let me be clearer about that. I'm saying, like, the line, you'll see in a minute when we draw more and more elaborate pictures, the line could, a line could stop because the line hits a charge. So, yes, the line could stop. Whether that means the field actually stops, I'm not sure I'm 100% saying that, but I'm saying that the I'm saying the line will stop, and I'll leave it at that for the minute. But yeah, you get it. I mean, you're hearing me. Yes. All right. So now I'm looking at the chat for answers possibly to my question. Ah, okay. I'm reading to myself. Ah, good. These are good guesses, and all these guesses, even the one, and they're different. All of these conjectures all indicate that you definitely get the question. So I appreciate that. Hold on. I'm just reading to myself for a minute. Ah, yes. Yes. Okay, I'm going to read. That's great. There's like four things in the chat. I'm not going to read the names. You should all give yourself credit, though. Seriously, like screenshot this. This is great. And again, not for the points, but also just it's a nice reminder to me that we really are together in this class. I really appreciate. So I'm going to read out loud, not the names, but the things here. They're all slightly different, but I think it may be what's on many of your minds. It says, one person says, like one person says the distance between the arrow the one person says the distance between the arrows on said lines, like if they're closer together, like they're closer together when they're closer to the charge. One person says, like one person saying they notice that the arrows themselves or the lines themselves are closer together when we're closer to the charge. So is that saying something? They're saying that, and then they were, that's my guess. That's a good guess. I love that emoji too. Then another person said, I think I understand what you mean is that the further the charge is, the weaker the charge, or the further away you are from the charge, the weaker the charge. Sorry, I'm slightly modifying what the person's saying. The further away you are from the charge, the weaker the field gets. While the closer to the charge, the field gets stronger. Like that's true. And the feature we could use is the arrows, meaning the more, so this person says, the more arrows in a certain region of the page, presumably, the stronger the field, and the less the arrows, the weaker the field. That's very similar to this. So, in a way, and there's other people too, I'll read them too. I want you to notice that what two people just said now was like very different words, very different personalities. And in fact, they were focusing on opposite aspects of what they were saying, but actually, what the both people said totally agree with each other and agree with the point. I'm going to read one more or two more and show you that it's all. So, yes, I mean, basically, I'm saying yes, even though those 2 points in a way sound very different. Then another person said, the lines are more crowded near the plus Q charge, indicating a strong electric field. Yes. And that is another way of saying what I think those other two people are saying. Yes. I'm going to put this in my words in a moment, but yes. And then also more arrows in the northeast corner, indicating a stronger charge there, or stronger, and I should say stronger field there. Let me say to everybody, because I see this slight misunderstanding or whatever permeating a lot of these. Like the charge is the charge. The charge is plus Q. It's like a proton sitting there. It's got an amount of charge that is what it is, and everything is based on that. But what we're talking about here is the effect of that charge on the world, i.e., we're talking about the field getting stronger or weaker. And what all of you are saying, including that last one I read about more arrows in the northeast corner, what all of you are saying is, okay, the length of the arrow doesn't really mean anything anymore, apparently, but the number of arrows per unit area on the page is what's indicating something. Like literally, people use different words like crowded or close together or far together. Some people said, oh, the farther apart the arrows are, the weaker the field. I totally agree. The farther apart, like as you get, I mean, as you get farther from the charge, the lines themselves are getting more spread out. The more spread out they are, apparently, the weaker the field. Or conversely, half of you said the closer they are, the more crowded they are, some people said. Good word. Or the less the distance is between the lines, apparently is the stronger the field. I 100%. Now the technical, so great. Yes, this is not a coincidence. And again, it's not just a rough idea. Like precisely speaking, from here on in, if you pick a certain area on, sorry, if you want to know how strong the field is in a certain point in space, you find the area on the page that maps to that point in space that represents it. You find some little piece of the diagram and you count the number of lines per square centimeter at that region of the paper. Like, and if everything has been drawn to scale in the first place, the number of lines per square centimeter, like per area, right? Because this is like a two-dimensional drawing, whether it's computer screen or piece of paper or what, the number of lines per unit area on the page precisely indicates the strength of the field in the space being represented. I.e., so I'm psyched, and you guys really should give yourself points for that. I mean, do the portal thing. I'm sure there's more than one, whatever. You know what I'm saying. So what it's saying here is the answer to the question in physics terms is the magnitude of the electrostatic field at any point in space is indicated by the density of lines at the corresponding point on the page. Density of line, crowdedness, just like you guys said, just the word we use in physics is density. And density means number of lines per unit area on the page. The denser the lines, the stronger the field. Okay, so now what I'm saying, we have 13 minutes. Now we have a mechanism for like reading these field line diagrams. Like now we sew up all the vectors to simplify and smooth out our picture and to start allowing ourselves to make pictures and understandings of things that we could not discuss before, really. And we shift and we say we're still all about magnitude and direction. It's all about magnitude and direction still. It's just that from here on in, direction is indicated by arrowheads, is still directed by arrowheads, but the arrowheads are not necessarily tips anymore. There are no tips or tails. There's just arrowheads. So direction is conveyed by arrowheads. Furthermore, the arrowheads could be found on a line that you're going to see in a moment, could be curved. So when there's a curve involved, we infer direction by imagining a tangent line to that curve. Okay, so that's direction. And magnitude from now on in is indicated by or represented by density of lines. When you see on a picture, I'm going to show you pictures in a minute, computer, well, yeah, like Google pictures in a second. This is not a paid advertisement. When you look at a picture, even if it looks really intricate or at first overwhelming or whatever, the idea is you look at the arrowheads to see direction of the field wherever you're looking, and you look at how crowded the lines are. It doesn't mean you have to do precise calculations at this moment. It just means qualitatively, if some region of the page has lines that are more crowded than another region of the page, then that region is indicating strong field compared to the other region. So that's the idea so far. In fact, since we only have 12 minutes now, I totally want to show you pictures. But because once I get into the pictures, I tend to get sort of bogged down in rabbit hole, surprise, surprise. I'm going to make sure right now to give you the punchline first. It's going to be a little bit abstract. I want to give you right now, I'm going to turn the page and give you right now the actual strict rules for drawing, for writing and reading these pictures. Now, the rules are maybe going to seem a little abstract until you look at some pictures, but I want to make sure you have them. So okay. So I'm going to give you some examples of field line diagrams, okay? And I'm just going to get them from Google Images like you could do on Earth. In fact, you could do it right now if you wanted to in your private IDO. If you want to just type, I'm not really suggesting that you do because we'll do it together in a second. But at any moment in your life, if you just type in E-field line diagrams or electrostatic field line diagrams, but make sure there's an E in it because there's other kind of fields in the world. But if you type in E-field line or even just E-field lines into Google Images, you'll get a whole slew of things that all look very intricate. in a way very beautiful, maybe in a way very overwhelming, but they're all very specific. That's what we're going to look at in a second. But let me tell you in advance how they're drawn and how you read them. So here's the rules for writing and reading E-field line diagrams. First, you choose a scaling factor, or the computer programmer chooses a scaling factor, like I was implying before. Like it might be like, okay, for every 1 coulomb of positive source charge, or every 1 Q unit of positive source charge, I'm going to draw 8 lines. Like you make a rule like that, a scaling factor, and 8 is often a good starting place because it indicates it's just enough to show you a pattern. So you make a rule like for every 1 coulomb of positive charge, there's going to be 8 lines coming out of it, and when you start drawing, you're going to draw 8 lines out of every one. If you have a 2 coulomb charge over here, then you would draw 16 lines out of that. And you'll see in the next rules, when you start drawing or computer programming or whatever, you draw the lines as symmetrically as you can. Like in this case of an isolated point, I literally put 1 in every direction. That's because space is the same in all directions. So you start drawing lines out of a positive source as symmetrically as you can. I'm going to look at the chat. Yes. Yeah, very good, Director. This is like a frame of reference as how you would do in graphs. This is like labeling axes. Yes, very good. I'm not our rules that I'm mentioning here are like a frame of reference as we would do in graphs. Very good point. Yes, and just as important. Yes, that's good. So that's rule number 1: is you pick a scaling factor. Then rule 2A is you start drawing lines. 2A, you'll see why A in a second. You start drawing lines, and where do you start drawing them? You start all lines from positive. Like, so you go to whatever positive source is, maybe there's more than one, but you go to whatever positive source is in your drawing, and you start drawing lines out of it. Like if it's 1 coulomb, you draw 8. If it's 6, if there's another one over here, that's 2 coulombs, you would draw 16. And you start drawing them as symmetrically as you possibly can. Like an isolated point literally makes radial lines, 1 in each direction. So all your lines have to start at positive, or they could come in from infinity. You'll see what I mean by that in a minute. And that gets back to the other private chat person. They could come in from infinity, which means like coming from the edge of the page and just, right? But they'll either start at positive or come in from infinity. You'll see what I mean by that in a minute. And then each one of these lines that you draw out now has to land at a negative. Like if there's a negative anywhere, you just connect the lines over to the negative. So in as simple and smooth a way as you possibly can, you just start connecting up positives to negatives. In fact, I'll even show you like like on the front page of this picture. This is kind of like your homework situation. Except these are equal charges. Like if I have a positive over here and a negative over here, I start drawing a bunch of lines out of the positive. Whoa, wait, sorry, one of them is wrong. Sorry. I don't know why that got backwards like that. I start drawing them out symmetrically from the positive, as symmetrically as I can. But then I start connecting them to the negatives. Now, if there's literally 8 lines that came out of the positive, if the positive is Q and the negative is literally also Q, like not 2Q or not 3Q or something, then every single line that came out of the positive could go over to the negative. So I start hooking them up. And you'll see in a minute, like I hook them up in the simplest, smoothest way possible. Where does this infinity business come from? Well, say there's any lines, you see like on the sides of the charges, for example, if there's lines that one line comes out of the positive directly to the left, but there's like no way to hook that to the negative. So, because the negative is on the right. So that line just goes on to infinity. Or similarly, there's one that has to come into the negative if I'm obeying my scaling factor, but there's no way it can come from the positive. So it comes in from infinity. So what I'm saying is, or furthermore, say the positive Q was twice the amount of charge as the negative Q, then you would have twice as many lines coming out of it, and half of them would not be able to hook up to the Q at all. Where would they go? They'd go off to infinity. What doesn't ever happen, we're saying, is you never have a line spontaneously start or stop literally on the page. No lines have tips or tails. They don't have beginnings or endings other than positive and negative charges. So you start just so the rule is, so 2A is start all your lines at positives. 2B is end all your lines at negative, or the lines can go on to infinity. Then rule 3, and we're almost done, believe it or not. Rule 3 is, as you saw from that picture, lines can bend now. Lines can curve, like vectors cannot, but lines can, because what you're really drawing is you're imagining there's all these vectors. There's vectors everywhere, and you're just sewing up the pattern of the vectors. So each vector might have been straight, but it might be in a pattern that's curved. So the lines can bend. If the easiest way to get from a positive to a negative, like, is to go like that, you do it. But what they can't do is cross. And I'll say more about why that is. Well, the simple answer of why they can't cross is each one of these lines is representing what happens at the end of the day when you add up all the vectors from everything. So yes, the lines like from something could cross the lines from something else, except that what that really means is the vectors from one thing were adding to the vectors from something else. And when you add the vectors together, you get a final vector. And sewing up all the final vectors is what these lines are supposed to represent. So the lines are what's happened after everything has been added together already. So lines never cross. The crossing already got taken into account. So lines can bend, but they can never cross. So then the final rule, we've 4 minutes left. The final rule is just, it's weird as it sounds, but you practice, you'll see after a while. All you got to do then is pick a scaling factor, start lines at positive, and find the smoothest, simplest, most symmetric way, like whatever pattern of line, like you just start drawing lines in a pattern from positive to negative in the simplest, smoothest, symmetric way you can that doesn't violate any of the other 3 rules, and that will be the field diagram, believe it or not. I mean, it takes some getting it, just like free body diagrams, they seem really intimidating at first to all of us. But after a while, there is only one way to draw the diagram. I'll say this, 3 minutes left. Maybe like some of you, I've never said this before. I want to admit something. With free body diagrams, for me personally, for the longest time, I always assumed that the free body diagram was something that the professor like drew once they already knew what the answer to the problem was, like that they drew it to show how they had added up all the forces and gotten answers and stuff. So I was always like, first of all, intimidated by it. And second of all, I was like, well, I don't even see the point. Like you're just drawing an understanding that you already have, but I don't have that understanding. So this drawing isn't helping me at all. If you've ever felt that, like I relate, but I'm here to say, no, it turns out once you learn how to draw free body diagrams, they create the understanding for you. They solve the problems for you if you follow the rule of the diagram. That's why we like them. Same thing here. It will all seem intimidating at first, 2 minutes left. But if you just follow the rules to draw the pictures, then you start seeing things in the picture, that you would not otherwise see. So with like a minute and a half left, but those are the rules. I've done what I wanted to do. You have the rules now. But look, here's some examples, possibly intimidating, of field line diagrams. Notice some of them curve, some of them don't. They're all very intricate. This thing where my arrow is right here, I'm doing this quickly because we only have 1 minute. This is what I was just talking about a second ago. Like this is your homework problem essentially here. Well, actually though, I'll go to this and then we'll be done. Actually, this thing right, actually this thing right here is really your homework problem, because you notice that is a positive near a negative, but where they're not the same. See, it says up here, unequal amount of charge. So the field lines get more dense. They're much more dense. Like there's a lot more field lines going into that negative than there are coming out of that. Okay, so it's the opposite of your homework, I guess. But the point is that they picked a scaling factor. I don't know why it's flipping back and forth. You picked the scaling factor, um, and followed it. So wherever you see regions of really dense lines, that's really strong field, and not. And I know it's 1040. We'll talk more about this on Monday, Tuesday. But one thing I want you to see right away, two things. 1040. One, um, it's very intricate, the drawing, yes, but it's an interplay of symmetry and asymmetry. Like it's intricate, but it's patterned. It's not random. And once you get used to seeing these things, you would see that you would come up with that pattern too. Maybe not as precisely, but you would. Number two, just a reminder, just like the homework, what is that showing? It's showing for any given point in space where where a test charge would be pushed and how hard due to the combined impact of the plus and the minus. It's not what the plus is doing to the minus, it's what together they are doing to all points in space. So it's capturing a lot of information in one picture that we couldn't capture with just one vector. Okay, but you've been very patient. It's 1040. If you have, I'm here for a couple minutes if you have questions, but you can go. I'm gonna so bye. Thank you. Your exam soon, I believe. Have a great day. I'm stopping the show. Okay, and there I'm gonna stop the recording, but I will answer any questions if there's it seems to be at least one in the chat. Oh, two. All right, hang on. Let me just close the recording. Yes, but have a good day. Hold on, hold on, hold on.